Hello, everybody. How many of you have heard about formal verification? Great. Okay, maybe I have nothing to say. So, I think a year ago, Tomer announced that we will build a formal verification tool specifically for Stellar. And actually, as of now, it is ready. There is an open version. Please come to the workshop tomorrow at 10:30. We also announced as part of that, and I think Tomer also announced last year, there will be a competition for security researchers to secure protocol built on top of Soroban. And this competition, Certora will award $200,000, and basically this will be awarded for finding bugs and writing rules. And stay tuned, we will announce. Okay. So this talk is actually a result of a huge effort. You see, I'm not here. Actually, I have not done anything, just the talk. So the person who actually did most of this work, and unfortunately from a visa person, she could not be here, is Chandra Nandi. She got a graduate at the University of Washington. She is an amazing researcher. We have a lot of people amazing. We also have Alex, Max, and Eric. Other people on the team I won't be able to explain, but all of us actually contribute to this tool that you can try. So what is formal verification? You know, you said you know, but in fact, and there will be another lecture after me, formal verification is sort of giving you a mathematical proof or actually showing that your code does as expected, or maybe finding violations of your program. So it's sort of the art of proving correctness of programs. There's a lot of history. I showed it actually last year. I don't want to repeat. But the idea is that formal verification, like many other fields of science, you go to different layers. At the beginning, you have the people who contribute most of the results. And then there is a dark period. Actually, this is where I started my career. And later on, after that, people build stuff. And this is actually what people, companies like Certora, runtime verification, we all sort of use the thing that people built. And most of them were built in academia or research institute, but they are now coming into industry in Web 2 and in Web 3. So for the purpose of this talk, actually, I want you to think about formal verification is something that increased the security of your code. And it's something that you can use in addition to any other method to secure your code. And here is a very, very nice tweet. Do you know this guy? No. No, okay. So do you know why he had this tweet? Does anybody know why he had this tweet? Why did he write this tweet? Or why? No. Look, it's very, very recent. Why did he do it? Everybody know this date is actually should be. This is after the Telegram co-founder was arrested. So basically he said, look, let's use formal verification to protect ourselves. So that's an interesting concept. I think the way we look at formal verification, and actually this is something that we learned from our client, and we have very, very good client in this domain, and one of the best one is Aave. And the guy here, Ernesto, I sort of showing, listen to his talk about Certora. And basically what he explained, Certora is helping them to cover a blind spot and to cover also unknown. Auditor help you with blind spot. They find the things that you know that you don't have to do. But the issue is, what are the things that you don't know? And this increases your knowledge. You can think about it almost like social science. This is the Juari. I don't know if you know. This is coming from social science, how you give people feedback. So formal method is somehow increasing your confidence on your code. So you get more confidence once you use formal verification, and this is why we want you to use the tool. So how does formal verification fit into the development process? It actually, you can use the normal development process with testing, with fuzzing, and everything. But the thing which is the most interesting thing is the specification. You have to write somewhere what your program is supposed to do. And then you can use testing, you can use formal verification, you can use everything. And in fact, the specification, the rules that we write, you can use them for many things, for testing, for fuzzing, and other things. And then, of course, you use it and you get more confident that your code behaves as expected. So maybe just sort of before I go into the technical part, I want to somehow give you some sort of things to think about formal verification. As I said, formal verification has a rich history, a lot of very good results, but a lot of people confuse many things about formal verification, and these are not the only confusion, but these are some confusion that at least I had in my career. So first of them, people think about formal verification as a bulletproof. They say, I formally verified it, and that's going back to the 60s. And there is a very nice quote by Donald Knuth. How many of you know Don Knuth? Okay, very few. So Don Knuth actually did most of the results in computer science, a professor at Stanford. And one of the quotes I like about him, he say, I don't trust this code, I only formally verify it. So I think the issue, formal verification, it increases your confidence, but who knows that your specification is right? So some level of paranoia, formal verification increases your confidence. People have done it in compilers, in many things, but you need to think about formal verification in a critical way. The other thing, and it may be related, that formal verification replaces auditing or testing or any other method that you do. And the question is no, it just complements it. It's another way. In fact, Certora does auditing and does formal verification, and these are complementary things. And also, formal verification, some people say that you have to come at the end. We don't think so. We think that you need to start as early as possible, and there are a lot of very good tools. For example, we even use, I don't know if Lido is one of the interesting protocols. We actually reason about their design using TLA. It's an open source system. So the idea is we want to actually check the code and check the design as early as we can. And maybe the last thing, and this is for the workshop, and this is our dream in Certora, we want to make formal verification a commodity. We do not want people, of course, people use us, and we have a lot of people in the team, and many of them have PhD. But the idea is we want everybody to use it. And the fact that we see communities like Cantina, like Code Arena, using our tool, it's great. We want to have more people using formal verification. Okay, so how does the Certora prover, the Soroban work? We write the spec in one file, and we write the code in some other files. The code is written in Rust. The spec, we decided to make it easier. It's actually written in Rust, but you have to be careful. It's actually interpreted a bit differently. But you can think about it like a spec, which is for the purpose of verification. And then the tool can give you a proof. That's very interesting. It can also give you what we call a counterexample. It's essentially a bug. It's a behavior that violates the spec. And you have to see if the problem is the bug in the code or a bug in the spec. But it gives you a bug. It gives you a violation. And unfortunately, it also can fail, because we are talking about a problem which is mathematically hard. So it can be that after a while, you just wait and you don't get an answer. Of course, we want to avoid it. And we are doing a lot of technique, and this is what we implemented this year. We implemented some techniques to avoid failures. So the nice thing about our tool, it's fully automatic. And because it's fully automatic, it integrates into your design like fuzzer, like compiler, like others. So every time you change the code, assuming that the specification did not change, you can rerun the tool. And we integrate into your CI with any CI tool, so you can run the tool again, and you prevent errors when you upgrade your code. So here is a very simple example by Lai. We have more example of real code, real Soroban. You see this is an increment function. The counter is read from the storage. The counter is increased, and then the counter is stored. All of it seems natural and easy. This is sort of the simplest program you can think of. But the idea is that in Soroban, the function interacts with the Soroban environment. So all of these functions interact with the Soroban environment. So what happened, even though this is a very small program, for us, when we do formal verification, it's actually a large program that is being handled. And on top of it, we actually handle the executable. So we actually handle a much larger program to verify. So we include, in fact, some kind of a model of it, and that's actually what we did. We have a model of the Soroban environment in our own language. And we faithfully implement this environment. So how do we write spec? So spec, you can think about it like thinking in Rust, but you have to have some kind of different interpretation. So here you see there is this CVT assert. It's an assertion that the code behaves as expected. And the spec is essentially a Rust function, but it's not checked at runtime. It's checked by us at the verification. So what happened? The user writes the spec, then it's converted to WASM, and then we have actually a decompiler. We are building a tool that compiles from WebAssembly into our own internal representation. Certora has its own internal representation. And then we actually apply transformation to make this internal representation easier for formal verification. And finally, we do what is called verification generation. Is essentially we compile your code into a mathematical formula that actually expresses all the behaviors. And then we can use open source SMT Solver. These are solvers that has been developed by academic institute and research institute, some of them together with us. And these guys can actually, and we have a lot of them, and we apply them. And they can give you a bug. They can also give you a proof that we convert into something which is understandable. So all this tool chain is something that we actually built this year, this part, to make this Soroban works. So how does it work? You see this increment function. And just to explain, you can, of course, test it, but we do this formal verification. So what does it mean? The first thing that you see about the initial value, we have this initial value. We are not making any assumptions about the initial value. This essentially means that you run your program on all the input. Of course, you say this is not doable, but we are not doing it actually. We have a mathematical formula that simulates that. This is called Havoc. We are essentially doing testing, but it's exhaustive testing, testing on all the values. And then, of course, if you look into a function, we prove all the properties of this function in all the cases. So let's take an example. You see this is the transfer function. And you see we had another command here. It's called CVT assume. CVT assume is assumptions. But again, it's not assumption. It's assumption that is given to the verifier. And this assumption tells the verifier, ignore these cases. So essentially what we are proving is what is called implication. We are proving if it's the case that 2 is not equal to the from, then the function behaves as expected. So the tool is actually proving you a mathematical property of your code. And it's interesting, of course, if you don't do it, if you don't have this assume, the tool will complain. The tool is very evil. Any bug that you have, it will find. So you have to help it with these assumptions to get this formal verification to work. And this is what we write, and this is what we expect you to write in the workshop. We expect you to write this specification. So maybe we show you a little bit more interesting example. We're actually building a more and more complex example. Here is a deposit function for the reflector. It's a recent client of us. And you see, actually, we simplified this code. And you see that now we have this snippet, and we're doing this activation. And we want to write the spec. So what is the spec? The spec is that the activation behaves as expected. So deposit retention fee must activate the subscriber. So it's sort of should say that the activation behaves as expected. And you see here we have this CVT assert that writes the specification. And then we actually apply that. The interesting thing that even in this small program, it's actually get quite a large WebAssembly code. It's about 1,600 lines. There is a lot of things that make the SMT life very hard. You have nonlinear arithmetic, interaction with the Soroban host, but still it verifies with few seconds. So what's the magic? What do we do? So we have to do a lot of things to make this magic. And of course, we are interested to handle larger programs, and then we need to do more magic. You also see another thing, and Johannes is somewhere sitting in the back. We have a nice UI. We want to make this tool usable, and the idea is you don't even want to read the WebAssembly. You want to go back to the Rust. You want to show something which is usable to you. So what is going on under the hood? So we have done a lot of things, both before this project and during this project, to make the analysis usable. And what we did, we have implemented algorithms that actually do transformation to make it more usable. And also the way we generate the SMT formula, we have a lot of clever methods. Some of them now are being redesigned in academia, but we are doing all of these things to make this formal verification feasible. So what do? We do all kind of simplification and make this, and also making the SMT solving in the right precision, so it gives you the right answer. So what are the techniques that we are doing? It's not a technical lecture, but still I want to give you the hints of it. We actually detecting some complex things that happen in the Soroban, for example, memcopy. We basically convert them in a way that's easier for the verification. We also detect initialization and make them easier. And we use actually interval analysis to actually make the memory analysis easier. And we have also ways that, I don't know, it may be confusing, but the idea is in formal verification, one of the things that's interesting, that sometimes verifying more is easier. So what we do, we call something which is called sound approximation. We don't know what it is, but we assume it's worse than it is, and still we are able to prove things. And that's actually how we handle nonlinear. A lot of things that people have shown that it's hard, we can show that it's, in fact, in practice, they're easy. So we have methods to go over complex things and to still prove them. So how does it work? You have this SMT solver, and this SMT solver, as I said, it can give you two answers. If you know in computer science, there is this problem called satisfiability. There is a formula, and you need to know if it's satisfiable or not. So you can think of the SMT as something similar. You have this formula, either it finds that it's feasible, or it actually says you that it's not feasible. If it's feasible, it means we find a bug. So if it's feasible, we find a bug. If it's not feasible, it means we found a proof. We actually can show you that the program behaves as expected. So for the feasible case, we have to go back to the source code. We have to show the person what is the call trace and actually what is the Rust code, which is actually corresponds to the program. And for the non-feasible, actually, we do something else which is interesting. We call this unsat code. The idea is we find the minimal code which is verifiable. So this actually gives you more belief in your specification, because we are worried, as we say, one of the problems of formal verification, maybe you haven't used the right specification. So we are trying to increase your confidence about the formal verification. So this helps the bug in the design. And it's also increased the trust in the spec. This is what we did. We implemented the result. You see this call trace here, some information about it. Here you have a barcode. Please scan it if you can, and please register to our workshop. And if you can actually register, and if you can download, and if you can start it before tomorrow, it will help us. Please, because we don't want to waste time, and our tool works over internet, so which probably means that you need to be connected to the internet. Bring your laptop. I've done this workshop before, and people come without laptop. You can work it on the phone, but this is formal verification. Again, it's working on the cloud on Amazon, so don't worry about computational costs. It's on Certora, but still working from the phone in formal verification is hard. Okay? So please bring your laptop. What's going on inside? I already said there's all these complex methods which are implemented. All of it is implemented here, and of course we will prove it as we go, and we want to hear your feedback. So the conclusion, bug finding is a hard problem, of course. Auditing is great by many teams, AutoSec, quantum verification, and us, but it's not enough. Fuzzing is also great, but it starts from the initial state, and we are starting from an arbitrary state, and this increases your confidence. And we implemented this automatic formal verification, and unlike tools like Kay, Cork, Isabel, Lean, these are great tools, but you need a PhD for them. And we want to make this formal verification something that everybody could use. That's our dream, and that's what we want. Sorry, I'm on time, Just come to the workshop tomorrow, handled by Johannes. Yes. Can I get one question? No, it is question. No? Okay. Thank you.